Hello guys, welcome to our channel. I am Lara, and in this video we are going to write the GAMS code for MCLP, so maximum covering location problem. Let's get started. So when we are writing a GAMS code, we are always first going to start with the indices. So we are going to assign our sets. So sets I. So I is going to be the index for the demand nodes. Which if you remember the video, it was from A to H. And then we had our facility locations, which was actually the same locations as the demand nodes. So we can still say A to H. Okay, so don't forget your Oxford commas after every cluster. So after we have assigned our indices, we are going to look at the scalars that we have. Scalars are numbers that do not change, like the amount of facility that we can open, it's always going to stay 2, or the coverage distance, maximum coverage distance, that's also going to be always 15. So that's our scalars. So our coverage distance, we are going to say DC, so coverage distance, which is 15. And then we have our p-value, so the amount of facilities that we can open, number of facilities, which is going to be 2. And because we're only going to have 2 scalars, after those 2, I'm going to again put a Oxford comma. Okay, so after the scalar, we are going to write our parameters. Our parameters here is the demands for each node. So hi, so demand. Okay. Oop. So for demand for node A was 35. Demand for the node B was 50. Demand for node C was 40. Demand for node D is 55. Don't forget the space. Demand for E is 25. Demand for F was 30. Demand for G was 40. And at last, demand for H is 25. So, oops, a table. What table? DIJ table. And what is this DIJ? It's the distance matrix. Okay, so let's write these things, the nodes E, F, G, H, and then A, B, C, D, E, F, G, H. Okay, so if we remember how this went, these parts, the rows, were the ones to be covered, and what you get in those rows were the facilities that can cover. So let's look at A. For A, this was 0. It's going to 999. I'm going to explain why it's going to be 999. And then again 999, and then 8, 14, 18, 22. 8, 14, 18, 22, 17. Okay. Okay, so what was these again? If one of these values are less than 15, this showed us that those places, those facilities could cover A. So that means A can cover A, of course, it can cover itself. D can cover A. E can cover A, but the rest cannot cover A. So the reason we put 999 in B and C is because in the previous video, when we solved this with hand, we saw that A and B had no connection. Because A and B had no connection, B cannot cover A, nor can A cover B. So to make sure in this system that A and B or other nodes that also are in this position cannot cover each other, we write 999, a very big number, so that the system does never consider that facility an option. So now I'm going to write the rest of the values and I'll just skip to the end. Now that I've written all the values, do not forget to put an Oxford comma, because that means that you are done with the table. There's nothing going to be included after this in this table. So what we did after this was creating an AIJ matrix. So what you can do for the AIJ matrix is you can create a table like you see here. But to show you a different thing, I'm not going to write in a table format. I'm going to write it in a different way. I'm going to write it as a parameter. So parameter AIJ, which was the coverage matrix, which meant that if the distances here are less than 15, it is going to be translated in an AIJ matrix as 1. So that means that facility can cover that node. Okay, so AIJ would be 0. When would this be 0? If it cannot cover. But what if it can cover? Usually AIJ is 0. But now I'm going to have to write a constraint, let's say, for when is it not 0. So I'm going to say AIJ. I'm going to put a dollar sign because there's a constraint going on. And then I'm going to write my constraint in it. So what is the constraint going to be? Dij is going to be less than or equal to dc. If this happens, okay, so if dij is less than dc, so if one of these values here is less than 15, this means that in the AIJ matrix, I can write 1. I can say that AIJ is 1. You can write it this way. You can also make a table. It's totally up to you. Then I have the binary variables, which was xi, and that was if the facility is open or not, facility open or not. And then we had zi, which was demand node covered or not. Don't forget your Oxford comma. Okay, and then we get our variable, which is going to be z. Oh no, not z, we can say z here. W, let's say. I can say z because I've already used it here. That's the reason. Have I used W? No, I have not. Okay. All right. Okay. So now to the equations. So my first equation is going to be the objective function, of course. And then I will see if coverage is happening or not. Coverage. And then we have our facility limit constraint. Okay. So objective. So let's see. V is equal to, we are going to write the objective. Now, what was it all? We are maximizing the demand covered. So sum, the demand was I, and then hash I, because that's the demand covered. And then we are going to multiply this with zi, because is that demand node covered or not? That's the first one. Okay, now we are going to write a coverage constraint. So why do we write this constraint? Because if a facility is not opened, you cannot expect that facility to cover a demand node. To make sure that does not happen, we write a coverage constraint. Okay, so we say zi, which was is the demand node covered or not? We are going to less than or equal to, because if one of the facilities are open that can cover the demand node, that's just enough for us. So that's why the less than or equal to. If it's 1, that's okay. If it's 2, then you cannot give zi more than 1. Okay, and then we're going to say, okay, and now we're going to write j, and then aij, if you remember the constraints from the last lesson, and then multiply this with x j. Okay, so what we have to include here is this I also has to change. To make sure that it changes, I'm going to add it here. So then the I can also change. Okay, and then we have the facility limit constraint. Okay, so this basically means that the facilities that are opened cannot be more than 2. Very straightforward, I think. So facility open or not, xi, so sum I xi will be less than or equal to p, because that's what we have said here, p equals to 2. And that's it actually. Okay, so I have just realized that I have written an xj here, xi here. It has to be xj because it has to do with the facility, not with the demand node. I apologize for that. So let's also change it here. Okay, and now our model is certainly done. We are only going to have to write the rest to solve. So model name is MCLP, and then we are going to solve it all, and then solve MCLP. We are going to use MIP. Maximizing this time, because we are maximizing the demand covered. Yeah, and then we are going to display YL and VL, let's say. Okay, let's run this model. Hopefully it will. There's a problem. Sure, let's look at it. So I have looked at the mistakes. There were some very absurd ones. I hope you have realized it when I was doing it and thinking, why are you doing this? So I have forgotten the sum here. Don't forget the sum, your constraints. And I have written y here. There's no y in this problem, but you know, it can happen. So now that we have got our now that I have solved my mistakes, let's look at the solution, shall we? So, okay, so this part shows us which facilities are opened. So E and F are opened, and opening E and F just covers everything, because you can see it is covered. It's covered, and the demand covered is 300. So thank you for watching this video. Hopefully you have understood a lot. And I'll see you in our next video. Thank you for watching.